These are the notes on wave behavior. So there are myriad different kinds of waves, but they all have similar properties. And then when the waves interact, they have similar behavior. So we are going to look at generic waves, and we're going to try to apply it basically to all waves. We don't care. Let's go crazy. So what does a wave have? A wave has a wavelength, obviously. And a wave has an amplitude, which is measured from the equilibrium, how much it's been displaced in one direction, not in both. But you can also measure the wave's frequency, and that depends on an observation. So let's say the wave is passing by you. It's how many waves pass by you per second. In this case, 2 per second. And we also call that 2 hertz. So these are some of the measurable things about a wave, and of course its speed or velocity. Those are the things you can measure about a wave. And those different properties can be related to each other. For example, the frequency is the reciprocal of the period, and you could even reverse that equation. I didn't mention that. You could say the period is the reciprocal of the frequency, obviously, and the wavelength equals velocity divided by frequency, or you could say the wavelength equals velocity times the period. That's another one that I didn't show you because it's really just a permutation of this exact formula. So these are the two we've been working with so far. Okay, now, what happens to a wave when it hits a boundary? Well, a couple of different things can happen. One thing that can happen is a reflection. Reflections are kind of simple. They're exactly what you think they are. The wave is going one way, the energy is being propagated in one direction, then it hits a barrier, and then it reverses and bounces off that barrier and travels in the opposite direction. Well, not always the exact opposite direction, we'll see in a moment. But this is a property that waves have. However, reflection isn't the only outcome. Another thing that can happen is that the wave can pass through the boundary into the second medium. So what can the second medium be? Well, if you're talking about springs, it could be one spring connected to another spring. If you're talking about things traveling, sound traveling through air, what happens when the sound gets to a solid or gets to water, gets to a liquid? That would be a different medium. That would be a boundary, right? And also with light waves, when they get to a different medium. So either going through air and then reaching the surface of a pool, that would be a change of medium. And then of course with seismic waves, every different layer inside the earth could be considered a different medium. So usually the main defining feature of the medium is going to be its density, okay? Unless you get into springs, and then it has to do with the coil and how rigid it is and all kinds of things like that. Okay, the interesting thing about waves is that more than one wave can exist in the same exact medium at the same exact time, okay? So they can sort of interact with each other. That is one of the most interesting properties of waves, is how they interact with each other. Now remember that the speed of a mechanical wave depends only on the properties of the medium it's traveling through. Like if it's traveling through a solid, if it's traveling through air, if it's traveling through water, if it's traveling through a spring, the speed depends on the medium it's traveling through. So it's a combination of the frequency of the oscillator, okay, and the speed that it's traveling that determines the wavelength. Here's an example of two different media. The plural of medium is media. Going from one medium to another medium, well, these are just two different springs. These are clearly different springs, and they have a different rigidity. They have a different K, for example. And if you send a pulse on the large spring, okay, well, then it reaches that boundary. Well, it keeps on traveling in this case. Most of it does, okay? But not all of it gets transmitted through that boundary. Notice how a little bit of it has been reflected. That's the before on the top and the after on the bottom. So the energy can sometimes do both. Some of it can be transmitted into the new medium, and you can have a partial reflection. So when you send a pulse down a slinky, like I'm going to do in the video at the end of these notes, what you'll notice, if it's attached to a rigid object at the end, if the end cannot move, then what you get back is an inverted pulse going in the opposite direction. Very much a reflection of the wave that went in. So it's going in one direction on one side of the slinky, and it's returning in the other direction on the opposite side of the slinky. So pretty much, in this case, what we're seeing is virtually all of the energy is reflected back, and it is inverted. Now, if you allow the end of the slinky to slide up and down, well, then that prevents the inversion, but that's a little more technical. So for the most part, if one end of the slinky is fixed, you will get an inverted pulse. So longitudinal waves have a very simple kind of reflection. They travel along in one direction, they bounce off the rigid end, and they travel back in the other direction. I will try to show this in the examples at the end as well. Not much to it, no fuss, no muss. Light waves can reflect off a mirror. Well, you've seen this before. You've seen light waves reflect. Now it's interesting, they don't always go back the way they came because it depends on what we call the angle of incidence. Okay, it incidentally is coming in at a certain angle, and we compare that to the normal. You should know what the normal is, right? Just like the normal force perpendicular to the surface. We also like to measure the angle of incidence from the normal, not from the surface, which seems the way people would guess that you would do it, okay? So if it comes in with a certain angle of incidence, it goes out with the same angle of reflection, okay? That is a property of light waves. Now, at certain angles, it might not reflect, depends on the surface. There are some surfaces that only reflect at certain angles, okay? But for the most part, this principle is obeyed with reflection. So that is the principle by which mirrors work, and any reflective surface, any shiny surface. And just remember that the light waves are not returning exactly the way that they came from, unless the only time they are is if they are arriving on the normal. If they're coming in perpendicular to the surface, well, then they return on the normal, exactly the way they came. But for the most part, they are not, and that causes the sort of left-right reversal that we are used to seeing in mirrors, because they're not going out the same way they came in, okay? Another property of light, which is even more interesting but a little more complicated, is refraction. Now notice this is different than reflection. Refraction occurs when you go from one medium into another medium. By the way, the plural of a medium is media, so it goes between two media, you could say. Now, there is a very specific index of refraction depending on which medium you are leaving and which medium you're going into. So there's a whole bunch of equations to deal with this, but the easy way to see this is if you look at water, okay, and objects that are under the water. You might notice that they do not appear to be where they really are if you're looking down from the surface. And that's because we're expecting the light to be traveling in a certain direction, but it's actually traveling in a different direction. What actually happens to the light when it enters the water? Well, actually, it slows down. Now, people say the speed of light is a constant. No, it's not. It's only a constant in an absolute vacuum in space. If light is traveling through anything, any medium, it slows down. Light is a little bit slower in air, by the way, than it is in outer space. Light is even more slowed down by water, okay, and let's say glass and plastic, anything that's translucent that allows light to travel through it, has its own index of refraction. So you can do all kinds of calculations to determine the angle that the light will travel depending on the angle of incidence, and you can determine the angle of refraction, and it's pretty much based on the densities of the two media. So if you're, for example, hunting for fish under the water, if you're in shallow water and you're aiming your spear, well, fishermen learn this pretty quickly. You don't aim your spear where the fish appears to be. Notice the diagram on the bottom. You have to account for the refraction. The only time you can is if you are looking along the normal line. Because notice, if you are looking straight down the normal, then there is going to be no refraction. If the light is traveling on the normal, it will continue to travel in a straight line. So that is one reason why when people are trying to spearfish, they aim right down below themselves instead of off at an angle. The further away from that you get, the more difficult it becomes. Okay, I'm not advocating that people go out and start spearfishing. I'm just saying that's a good example of where refraction comes into play. And if you have a fish tank, you can try to observe this. Try looking down from different angles and try to figure out where the fish really is. Okay, or if you have a bucket, you could put your hand in and look how it appears differently under the water than it does out of the water. There's a lot of ways to see refraction. Another super cool thing that waves do, other than reflection and refraction, is superposition. Superposition means to put on top of each other. So if there are two waves traveling in opposite directions, or even in the same direction, and they line up with each other, well, they interfere with each other. They sort of mess with each other. And that could be positive, or that could be negative. So they can either combine into a much larger wave with a larger amplitude, both up and down, or they can sort of negate each other and totally disappear. Both of those are possibilities and everything in between. So it depends on the direction the waves are going, the phase they're in, the amplitude of the waves, but it's a very simple equation. It's basically just literally adding the amplitudes. So if two waves are in superposition, you literally add both amplitudes to get the new amplitude. It is that simple. There's not too many mathematical equations that work out as easy as addition, okay? And of course, if it's the crest of one wave and the trough of the other, and they're the same amplitude, they actually, you would add them, but one would be negative, and whoosh, you would get zero. So it is possible for two waves to be superposed on each other in superposition and completely negate each other. It's really interesting how this happens. So one property of wave resonance is what we call standing waves. So I'm going to try to show you a few standing waves. I'm going to show you actually two of these three. I'm going to try to show you two of these three on the little video at the end. So standing waves are really cool, and they're a property of most waves. So because waves will interfere with each other, if you keep producing waves on the same frequency and they begin to interfere with each other, okay, what you can do is you can build up a very large amplitude compared to, let's say, the amplitude of your oscillator. Now, this can be a good thing or this could be a bad thing. It depends on where it's going on. Okay, so this can be a good thing. It can create music, or it could be a bad thing, like with the very famous Tacoma Narrows Bridge. This is one of your classic examples of resonance gone wrong. They built a suspension bridge up in Washington State, and they built it in a very windy corridor. They did not realize that the wind would be coming in a certain frequency. In other words, the wind rounds a corner, and then it gets cut off, and then it rounds a corner again. So basically, it would come in with a certain frequency. Because the wind was coming in at a very specific frequency, it wound up oscillating the bridge, causing the amplitude to increase more and more. They nicknamed this bridge Galloping Gertie, okay? And eventually, sadly, this entire bridge collapsed because of the resonance. So that's an extreme example. There was another example in the early 2000s. They built a little pedestrian bridge in London that had a similar problem. Okay, so I'm sure you could find videos of the Tacoma Narrows Bridge or the London, I forget what the name of the bridge was, but it was a kind of a very modern style bridge that they didn't account for the effect of wind. So wind, and I didn't describe it exactly perfectly, but the way the wind can oscillate cause the bridge, and as long as that continues with the same frequency, it can build up a very large amplitude, and that can cause a lot of strain on the bridge, and eventually, in this case, sadly, a collapse. Look it up. I don't have a video of it, but you could look it up. So what happens when two waves are in phase with each other? By the way, when they're in phase, that means the crests line up, the troughs line up. Well, when they're in phase and put them together, you add the amplitudes. That is called constructive interference. They combine and build a bigger wave. Now, when I say bigger, I mean it has a greater amplitude. So it goes up more and it goes down more. What about if the waves are out of phase? This is about as out of phase as you can get. Okay, 1/2 wavelength out of phase. So now we've got the crests lining up with the troughs. So what happens when we combine these waves? You probably guessed. This is called destructive interference. Destructive. So what it does is it completely cancels out both waves. Amazingly, it works out almost perfectly if you get them exactly 1/2 of a wavelength out of phase, as long as they have the same amplitude, that is. Destructive interference. And then a lot of times what we wind up getting is sort of in between, where it's not exactly constructive and it's not exactly destructive. It's basically they're just out of phase with each other. So in this case, what we get, what do you think you're going to get? You get something like this. So this is called out of phase interference. And then what can happen is it can go down and then back up and then down and back up, sort of pulsing. Okay, so we get all these cool kinds of interference, and sometimes it happens because the waves are traveling in opposite directions, and sometimes they're traveling in the same direction, but in either case, you can get interference. Now, standing waves are a cool example where one wave is traveling in one direction, and then the reflected wave is traveling in the opposite direction. And if those wind up in phase with each other, what you wind up getting is a standing wave, where it appears like the wave is just sort of sitting there, standing still, which is why they call them this. Now, standing waves have nodes and they have antinodes. I'm going to show you these in my little video. The nodes are where it's basically doesn't appear to be moving at all. And the antinode is where it has the greatest displacement, where it's moving the most. I'll show you these on my little video. So I'm going to show you a standing wave where I start off by generating a 1/2 wavelength standing wave that takes the entire length of the spring. Then I'm going to double the frequency of vibration, just moving my hand side to side, and that will produce another node and another antinode, and then what we will have is one full wavelength. Then I'm going to try to produce one that has 1.5 wavelength, and you can keep on going with any addition of another half wavelength. So you could do 2 wavelengths, you could do 2.5, and so on. So here you see examples of standing waves. Now the one at the bottom is a little bit harder to produce with the equipment that I have, but you can see that you could obviously keep on going. The one on the bottom there has 2 wavelengths. Okay, so you might say, well, that's weird because it looks like there's 4, but remember, each one of those is only half of a wavelength. Each one of those antinodes, okay, is only half of a wavelength. So 2 of them is a wavelength. So the one on the top is a 1.5 wavelength standing wave. Okay, so now we've got a Slinky. I found a bootleg Slinky. This is not the ideal one. And you're going to be able to see how Slinkies can represent waves. I've got it attached on this end, so it's stuck in one place. And we can see a few things here, like longitudinal waves. Let me try this. You see that? That's a longitudinal wave. Notice that I send a little pulse through, and then it reflects back. And then try a few more of those. Now it's a little bit harder to show a transverse wave with this, but I could show a pulse. Watch what happens with the pulse. I'm going to move it slightly this way and then jerk back into place. Do another one. So if I make this longer, it might be more visible. So you might notice that I'm sending a pulse going in this way, but then it's coming back on this side. That's what happens with a reflected pulse. Okay? Now, the other cool thing I can show you is I can show you standing waves. Okay, so standing waves, I can get one going that has 1/2 wavelength. Remember, a half wavelength is exactly what it sounds like, half of a wave, either the up or the down part. So let's see, if I get a standing wave, look, this is a 1/2 wavelength standing wave. And notice I'm barely moving my hand, not very much, but the wave can go much bigger. Okay, the wave can go much bigger than I'm moving my hand. And then this is called a node right there, and a node, and this is called the antinode, where it's got the biggest range. Now I'm going to try to do one wavelength. I'm going to go a little faster, like this. Now this is a one wavelength standing wave. Look like you can see the whole wave. At any moment, it looks like if you blur your vision, you can see the whole wave, right? And this one has 3 nodes and 2 antinodes. It's kind of hard to maintain it while I'm doing that. Now I'm going to increase it by another half a wavelength. Let's see, can I get this one going? Now I'm getting a little chaotic here. See that chaoticness? I got to get it right at the right rhythm. Okay, let's see. There we go. There we go. It seems to be dying out. I can't get it. There we go. So then this would be 1.5 wavelength. 1.5 wavelength. It's a little blurry if I go that. If I do it too slow, there's too much friction. And you can also see examples of reflection going on here. Now, why does a standing wave happen? Here's one I can maintain pretty easily. The reason a standing wave happens is because the wave reflected back is sort of in sync, in phase with the wave going in, so they constructively interfere. All of these other weird ones I'm getting in between, okay, they don't constructively interfere until I get to multiples of a half wavelength. I can't believe I'm having so much trouble doing this one. I think it's because of the friction with the table. Okay, maybe I'll make it a little longer. Okay, so then, and then theoretically you could keep going, keep adding half of a wavelength, but this one's kind of short. It works a little bit better if you make the Slinky really long, but this is on a countertop, and if I did that, if I tried to do that, you would only see a portion of the wave. You would only see a portion of the wave here, okay? Also, there's the element of friction with the counter. So again, here is a pulse, a longitudinal wave, traveling through and back, and if it was a sequence of those, if my hand is my oscillator, if I was going back and forth and back and forth over and over, then I would generate a sequence of them, of course, and there would be sort of a frequency and a period, but then the velocity that travels depends on the medium. The velocity that the pulse travels depends on the spring itself. But then, of course, I can change, oh, there we go, that was, why am I doing it so easily now? I can change the frequency of the oscillator, okay, and that, of course, changes the wavelength, but not its speed. So now you can see why springs and waves are related. So that is the end of the notes on wave behavior.